Hello and welcome to webinar series on mechanical engineering. We're extremely thankful to ISTE for choosing us as their knowledge partner for this webinar series. In fact, this webinar series is exclusively designed for students, research scholars, and junior faculty. In fact, we would be adhering to the BTech curriculum across the Indian universities in mechanical engineering. And the objective of the webinar is to provide conceptual clarity from the product development perspective. And also, we would be looking at the readiness of the student from the perspective of competitive exams, research interviews. So a lot of situations drawn from competitive exams, research interviews are also going to be discussed apart from the standard case studies that are relevant to contemporary industries. So let's check it out what is in store. On behalf of ISTE and Innovent, I would like to profusely thank all the participants. I know audiences are from different quarters and hope we would be able to satiate every audience. And before I begin the webinar formally, I would like to thank the chairman ISTE, Dr. Suresh, and also my chairman Sivasubramanian, who have put in a lot of efforts to see that this webinar series is realized. And we assure you that in the next 1 year, we would try and address all the fundamental areas of mechanical engineering. So let's get started. Thank you one and all for your time. Hope it would be really fructifying for all the audiences. Thank you once again. Now let's start with the agenda for the day. And as far as the agenda of this webinar goes, we would be giving you a brief introduction on vectors. And then we would look at typical facts and formulae. And then we'll take up case studies, and in between, if there are any relevant gate questions for mechanical engineers, that is also going to be discussed. We're not trying to trivialize by picking up problems from competitive exams. Rather, we are seeing all that in the light of requirements for product development. In future, perhaps we would also try and exploit the technology for live interaction. But since we have audiences from different quarters and different levels, we would be collecting all your doubts pertaining to this webinar on these email IDs. So please carefully make a note of these email IDs so that you can send in all your queries, such that all your queries will be given a very, very detailed reply within a week's time. And let me also tell you that whoever is going to register for certification will have to sit an assessment after completion of every topic. In fact, we are beginning with engineering mechanics. That means there would be an assessment at the end of this chapter. And the first thing we are starting with is vectors for mechanics. Now, one of the ideas as far as academicians and industry experts are concerned, mathematics must be a natural requirement. In fact, we are fundamentally opposed to the idea that mathematics is learnt as a separate subject. Since mathematics is the language of physics, it must be a natural requirement. And today we are going to discuss vectors, which is relevant to rigid body mechanics. And you would appreciate that even if you refer a standard book on mechanics, say for example Dynamics by Greenwood, you would appreciate that even the intermediate dynamics is treated only with the help of vectors, matrices, and basic calculus. So let's check it out. Let's begin with a very simple example. You can see that as the cyclist is cycling with certain velocity, the wind which is in fact falling vertically is being perceived to be falling at an angle, right? Here we are talking about the relative vector. That means his observation is that the rain is falling at an angle because of his velocity. And this is the basic velocity triangle concept that you have learnt for relative vector. And as the speed of the cyclist increases, what happens? The inclination of the rain with the horizontal decreases, and at one point, if he is at a very, very large velocity, he would feel that as if the rain is coming from the opposite direction. So now let's start with a very simple puzzle in vectors. Now let's say that a car is starting from this position, that is from this particular point, and this makes an angle theta with respect to x-axis, that is the position vector that is joining the origin and the point where the car is stationed, makes an angle theta with respect to positive x-axis, xyz. And let's say a ball is rolled and the car also simultaneously starts. A ball is rolled from the origin and the car also starts from this particular position, and both of them meet at position A. If somebody asks you what is the direction of the ball that is observed by a person in the car, it is very, very obvious, but many youngsters struggle to answer this. You see here, the question is so beautifully designed. This is a typical IIT JEE question. You can see that this is the velocity vector of the ball, this is the velocity vector of the car, and the difference of these two velocities is what is observed by an observer inside the car. That means, again, we are looking at the velocity triangle, right? Now let's move on. Let's look at some typical applications. When it comes to rolling, again we use vectors, and by using vectors you would have proved in your +1, +2 that this point O is the instantaneous center of rotation. When I say instantaneous center of rotation, that point is characterized by zero velocity. Why is so? Because there is no relative motion between this roller and the ground. And as a consequence, you would see that V is equal to omega r, where V is the velocity of center of mass, and omega r is the velocity due to the rotation. So it's a 2-degree freedom system. So this is, let's apply this particular concept to a gate question. Now you see here that since this is the instantaneous center of rotation, this is a fixed point, and if you seek velocity at any point on the roller, it is quite simple. It is omega cross the position vector, right? Omega cross the position vector. So the highest point and the lowest point would obviously have a velocity difference of 2 omega r, because if you go by this, the topmost point, the magnitude of the position vector is 2r, and since omega is constant and they are perpendicular to each other, if you take the vector product, the topmost point is characterized by 2 omega r and the bottommost point is characterized by zero velocity. Of course, it's an elementary concept, and if you look at the typical question of gate, you can clearly see that the bottommost and the topmost point have got a velocity difference of, this is in positive x-axis, this is along negative x-axis, so the difference in velocity is 2v, and that is equated to 2 omega r, because this is perfectly rolling, gate 2020 question, and therefore what happens is 3v by 2r is the value of omega. If you understand this simple concept, the time that you take to answer this question is approximately 5 seconds. All right. Now let's mature the discussion slightly and look at this particular example. You see here, I want to calculate the angular velocity of this particular link, and I'm not going to apply anything new. The velocity difference between this point and this point, that is the relative velocity, is nothing but omega into the position vector, what I discussed in the last slide. See, it is applied here. Further, we can use vectors in number of areas. I'm going to walk through before I get into a detailed devoted discussion for vectors. You might have heard in satellite industry that especially for low Earth orbits, satellite stabilization is done via gravity gradient torque. Okay, gravity gradient torque. Most of you would have heard this. That is, any body which is asymmetric would experience, for example, if I take this point and if I take this point, let's call it A and B. If this experiences a certain gravitational pull and this experiences certain other gravitational pull which is magnitudinally lesser or greater, then what happens is this entire satellite is subjected to a torque, and that torque is called gravity gradient torque. You can see here, though this requires further simplification, I have chosen a mass element here. Hope you are able to see that. And I have written an expression for gravitational torque because the resultant vector of the distance from the center of the Earth to the center of mass and the distance of the elemental mass, that is, this is the vector from the center of mass of the Earth, and this is the vector of that elemental mass from the center of mass of the satellite, and this is nothing but the gravitational force. You might have seen this expression r square. You see here r cube because I have expressed this in terms of vectors, and since it has to be only the direction, I again divide by the magnitude of the vector, so that is where I get this particular vector, and that cross product with the position vector x, I in fact end up getting the gravity gradient torque. In fact, if you simplify, you will get a very, very neat expression, and we would make use of the fact that gravity gradient torque is proportional to the principal inertia differences about any two axes. For example, it could be proportional to Iy, Ix, or it can be proportional to Iz minus Iy, and of course in one of the directions, that is your direction, or your inclination does not influence this. We'll get into that discussion in some other webinar when it comes to dynamics, but we are talking about vectors. And similarly, if you look at the Coriolis effect on a missile, if you launch a missile, it misses the target by certain value, and that is because of the Coriolis effect. The method that we have given here to assess the deviation is a simplified one. What we say is, per se, the velocity of the projectile or the displacement of the projectile is not affected by Coriolis force. Rather, the Coriolis force provides an additional displacement because there is angular velocity of rotation of the Earth, and there is velocity vector of the projectile at every point. And if we account for these two, the Coriolis effect provides an additional displacement, and that is where it would help the missile miss the target, and that has to be accounted for if it is if the range is significantly large. Otherwise, the contribution by the Coriolis effect is not that great. In another example, you can see that a large weight is hung from the boom, and you can in fact calculate the moment contributed by this so as to assess the stability of this particular vehicle. Again, the use of vector product. Again, to derive the general mass moment of inertia tensor, what we call IXX, IYY, and IZZ, if the body is not symmetric, you would also get the cross inertia products also. We'll discuss this in detail when it comes to dynamics. I'm just telling you that using basic vector product, you are actually deriving this particular matrix also. So this matrix can be derived using basic vector product. That's what I'm trying to impress upon. I'm just going through various applications. Now, if you look at this particular slide, again, the vector product is used to compute the torque contributed by movement of momentum. That is, as the gas or fluid flows across the blade, what happens is there is a momentum change, and that momentum change would bring about a torque at the bottom. And you can see that for a blade, only the radial component exists, that is moment arm, and these two don't. And as a consequence, you would get two torques. One is the tangential torque, which has to be absorbed, and of course the axial torque, which is the useful torque in driving the turbine. So again, here moment of momentum of the fluid is again computed using vectors. One more important situation: whenever the rigid bodies are undergoing motion, and if they are associated with unit vectors, then what is very, very important is that those unit vectors also are differentiated because they are associated with rigid bodies. For example, you can see that the wheel is not only spinning about this particular axis, that is the ith axis, but about the vertical axis, that is the y-axis. It is also precessing, right? And therefore, what happens is the spin vector has to be differentiated, and we'll look at this particular fact. In fact, if you look at this example, the mass is moving with velocity v, and then what is happening is, if you differentiate it, since it is also spinning, you get two components of acceleration, the centripetal and Coriolis. This is where differentiating a unit vector becomes very, very important. Incidentally, note that if you differentiate a radius unit vector, you would in fact end up getting omega into tangent unit vector, and if you differentiate a tangent unit vector, you would get negative of the radius vector, and of course multiplied by omega, the angular spin rate. All right. So we can find more number of vector applications. You can see here that radius of curvature for a general curve is determined using vectors, and also the torsion, that is twisting of a particular path or a particular curve, is determined here. And these are very, very important if let's say you are negotiating a terrain on a particular planet, where if you want to assess, you will have to characterize that path with both curvature and torsion so that you can control your motion of your vehicle. Okay, these are slightly advanced concepts which we are going to cover through the course. Now, these are some typical dot products which you have learnt in your school also. But one thing I would like to emphasize here, that this is an important one, because you can see that L here we mean to be the angular momentum. Some people represent this by H also. And what is important is that if the angular momentum direction does not coincide with the direction of spin, then what happens is that leads to an unbalanced torque. How to go about this? We would look at it carefully, and then you also look at certain typical vector products which we saw in rolling, and then this was the moment of momentum which we looked at in a typical turbo machine situation. This is again the torque expression, and similarly you can have Coriolis, you can also have gyroscopic couple. And one of the advantages of especially dealing with these inertial couples, gyro, Coriolis, the advantage is you are able to get the direction of the couple and hence the reaction couple, because whenever you're let's say you're dealing with gyroscopic couple, you're interested in the reaction couple because it is an inertial couple. It's a non-dissipating damping factor in vibration. Okay, that should be carefully understood. We'll discuss that. But then the point I'm trying to say is if you use this formula and then derive any inertial quantity, you'd be rest assured that you are getting the right direction. Okay, from elementary problem solving perspective I was emphasizing. And please remember that before we go in detail, there are two categories of vectors. One is of course the axial vector, and another is the polar vector, right? The direction of polar vector is natural to reckon. That means if I say a bus is traveling with certain speed along certain direction, then that is very, very natural to reckon. But as far as the axial vector is concerned, let's say that if I consider a roller rolling on a ground ideally, then what happens is if I consider omega, and that omega has to be represented, since it is clockwise, we would use a right-handed screw principle. That means omega can be represented by minus omega k. That means omega is along kth direction, minus kth direction, and the direction is coincident with the axis of the roller. Okay, this is the omega angular velocity vector, and that is represented here. And sometimes you may also want to split the angular velocity vector. Look at here. This is capital omega, that is, it is going around about the vertical axis. At the same time, it is also spinning about its own axis. And here, you can in fact split omega to be omega cos theta along the x-axis, and then the vertical axis thing would be omega sin theta, right? And since it is rolling perfect, if you take the moment about this particular point of this vertical vector and then try and equate that to 0, because whenever something is rolling perfect, the point of contact, since it is in contact with the earth which is at rest, it has to be 0, and you would easily deduce that omega by sin theta is equal to minus omega, and this negative sign is important. That means the sense of this omega and sense of this omega have to be opposite to each other. Suppose this is clockwise, this has to be counterclockwise, and that is one example where we represented axial vector. We also split and applied the axial vector at certain point. And if at all, if you are interested in a general point, you can investigate, develop a position vector, and then differentiate once or twice depending on whether you are seeking velocity or acceleration. And again, this is a classical situation. Now let's move on. Now let's consider one particular case which can be applied to the several product lines across the industry. This is very, very important. So follow this particular derivation carefully. Though it is a very elementary discussion, it is applied in several situations. Now, as I said, let's consider a spin vector along the vertical direction. Let's also consider a general vector which makes an angle theta with respect to the spin vector. Now, if I split this particular vector along the x-axis and also along the y-axis, that is, if I take the components, then you can see that it is represented, that is, along the x-axis, ax is the component, and along the y-axis is the ay, okay, the component. Now let's look at differentiating this. All right. Now, I'm going to give you a very, very basic observation, physical observation. I'm not going to be a purist here. Now here, you see here, when I project the vector, or when I take the component of this particular vector on the y-axis, that vector is along the spin direction. That is, it is spinning in the anti-clockwise direction. That is why the vector is along positive y-axis, to be noted carefully. When I split and take the component of A along the vertical axis, what happens is the vector does not change with respect to time because it is coincident with the spin axis. But if you looked at the component of vector A, which is along the y-axis, is spun around. Okay, if you looked at the top view, it is spun around with an angular velocity omega because it is perpendicular to the direction of omega. Right? Let's put this physical observation into a mathematical expression. When I differentiate it using chain rule, the first thing I get the rate of change of Ax with respect to time along the ith direction, and the magnitude of A along the x direction, and rate of change of the unit vector, because as it is spinning, what is happening is this vector is also, if you consider that as radial vector, it is also undergoing change. And then of course the rate of change of Ay with respect to time. And when I differentiate Ay, I will also have to differentiate the jth vector. But then I clearly told you that since the jth component is along the spin direction, it is constant, it is not undergoing change. So that goes to 0. And if I assume that even Ax is not changing with respect to time, and Ay is also not changing with respect to time, then what happens is I am left with only one quantity, that is Ax into di by dt. Now we can clearly see in this diagram that as A is spun, and this small change is given by Ax into delta theta. And if I take this rate of change of A vector when it is spun through a small angle delta theta, this becomes the rate of change of that particular vector. And that change, observe carefully, if you looked at the top view, it is happening into the plane of this particular PPT. That means it is along the negative kth direction, that is negative z direction, and therefore but this is nothing but omega. So when I actually compute, neglecting the magnitudinal changes, only the direction change, if I compute, I get this quantity, and this can be easily converted into vector product. And you see that the negative sign is justified because when you are taking vector product omega cross A, the angle is measured from omega to A in the clockwise sense. So therefore this vector product is justified. So any vector which is at an angle theta to omega, and if that is spun, then the vector product is given by omega cross A. And let's apply this to angular momentum being spun by this omega, assuming omega to be constant. Let us take this to be the practical case. Of course, this diagram is drawn to give you that visualization. When the radius vector is being spun, you can see that the change is taking place in the negative kth direction. And of course, here the spin vector is capital omega is kept constant. Okay. Now, where and all this concept is applied? See, this is applied to a rotor or a long compressor assembly, let's say, or it could be a disc or it could be a stick. When I say stick, it's a long, thick cylinder. When I say disc, it is a thin cylinder. And when it is mounted at an angle theta to the direction of spin between bearings, it does experience a couple, unbalanced couple, and that happens because the angular momentum of this rotor does not coincide with the angular velocity. And also, you look at this particular example, a heavy rotor which is hung at the end of a light cantilevered beam, and because of the self weight, this also makes an angle, and again it goes into a conical motion, and again here we are talking about the gyro effect. Okay, in most of the literatures that a couple experienced by the overhung rotor is called gyroscopic couple, but may not be true, but again that is equivalent to an unbalanced couple. And you can also see that that unbalance, this unbalance, whatever I'm talking about, is equivalent to this. That is, the different parts of the rotor experience centrifugal forces which go to constitute the couple. In fact, from centrifugal force moment also you can derive that particular couple. And you can see here a typical diagram where the angular velocity and the angular momentum have a different inclination, and this also leads to an angle called nutation angle, and in most of the satellites either active or passive nutation damping is used to control this. And all these things can be handled with one formula that we just derived, that is omega cross A. And if I suppose that my A vector is angular momentum vector, it is this which actually goes to control all of this. Let's try and compute this particular thing. Now, let's look at this particular case. The angular velocity of this rotor is along a particular axis, but you can see that the vertical as well as the horizontal inertial axis, principal inertial axis of the rotor are actually undergoing a conical motion. That means the angular velocity is not changing with respect to time, but since angular momentum is continuously changing direction, okay, if I call these are body axis, body fixed axis, y and x body fixed axis, and whatever momentum associated with these axes are constantly undergoing a change in direction. See, observe this interesting fact. Whenever I differentiate a vector, I differentiate its magnitude, that is let's say h, and then I also differentiate its direction. Let's say if r is the direction h is associated with, that also undergoes a change. So either the rate of change of magnitude leads to angular momentum, leads to a torque, or rate of change of direction leads to a torque. That is the beauty of the vector. Even for example, if I consider a circular motion, if I consider the tangential velocity at any point, then that is represented by Vt. That means if I get the rate of change of magnitude of the velocity, then that leads to tangential acceleration. And if I differentiate the tangent vector with respect to time, that leads to what is known as centripetal acceleration. Okay, and that is radially inverse, and that also goes to verify the mathematical fact that if you differentiate the tangent unit vector, that gives you negative radius unit vector multiplied by omega. So therefore, if you take care of mathematics, it takes care of the physics. If you take care of the physics, the mathematics is automatically taken care. So that's very important. Now, since the rotor makes an angle with respect to the axis of spin, let's say this is theta, and this is the transversal mass moment of inertia axis, and this is polar inertial axis, polar mass moment of inertia axis, and I have represented both on a diagram. This is rotor's polar mass moment of inertia axis, and this is the rotor's transversal mass moment of inertia axis. And let's say that this is theta, which you see here, because you can clearly see that the angular velocity vector omega makes an angle theta with respect to the principal inertia axis. Here I am referring to polar mass moment of inertia axis. And since angular momentum does not coincide with omega, let's say it makes an angle phi. Now let's apply the formula that we just derived, right? What was the formula? It is omega cross h. And that could also be written as omega into h into sine of the angle between the two vectors. Here it is nothing but phi minus theta. And if I expand this using elementary trigonometry, I would get keeping omega outside and taking h inside, sine phi into h, and then of course cos theta, and then minus sine theta, and then h multiplied by cos phi. You can clearly see that h into sine phi is nothing but the projection of angular momentum onto the vertical axis, and h into cos phi is nothing but projection onto the horizontal axis, that is polar mass moment of inertia axis. And how do you calculate the angular momentum? It is nothing but mass moment of inertia multiplied by angular velocity. And you can also see that angular velocity being an axial vector, that can also be split along the polar inertia axis as omega cos theta, and that along the vertical, that is transversal inertia axis, as omega sine theta. Now if I were to replace sine phi and h, and h by this particular definition, and if I represent the transversal inertia as it, and since it is omega sine theta, and then of course here I have cos theta, and similarly when I did that for the horizontal component, h cos phi can be replaced by ip omega into cos theta. I get omega, there is one more omega here, omega square, and if I assume that this particular angle is very, very small, in some axial pumps the rotors are deliberately given a large inclination. You can go and research that, but in case of standard rotors, this is inevitably because of some coupling error or some geometric tolerance error. Very important, we are going to discuss that in future. So that being the case, theta would be generally small. As a consequence, cos theta goes to 1 and sine theta goes to theta. Hope most of the industry guys would be able to spontaneously recognize this particular term, and this is nothing but the unbalanced couple in a rotor, and it is very, very important that this is determined whether this is in what direction is important, because this is determined by the nature of the rotor. If it were a disc, then it would be different. Since in rotor dynamic language a thick long rotor is called a stick, it has this particular expression. Otherwise it would have been ip minus it, and there can be some extraordinary case where the geometry is designed such that it is approximately equal to ip, then the couple does not exist at all. And this couple is going to be provided, of course, by the reactions on the bearings, which are of course the rotating reactions, because if you divide this couple by the bearing span, you would get those reactions. Obviously the reactions have to be provided by the bearings. And one important thing, in automatic balancing machines, the rotating unbalance is in fact measured at the rotors. If the rotors are rigid, then you can use force transducers to measure, and then you can automatically correct that particular unbalance. A very, very important expression. And also in case of stick, that is a long rotor, this is pressing away from the equilibrium, that is it is tending to increase theta, and it is the other way round for disc. And please youngsters who are watching this research, why for disc balancing, vertical balancing machine would suffice, or I am talking about a self-centering effect, which you can go and research. The beauty of the physics and maths is you started with a very, very basic vector product, and when you applied it to a practical situation, so many facts start tumbling out, and that is very, very important. And of course, you can also research detumbling of the satellite, which is again a very, very important phenomenon. Now, when it comes to competitive corner, we have chosen one standard case study that is from a research interview, which is very, very interesting. Now, let's start with a typical mass moment of inertia tensor for a cube which is located in the Cartesian system with one of its corners coinciding with the origin. Now, if I seek the eigenvalues, in fact, I would get two eigenvalues. That is, one eigenvalue is of course obvious to reckon. That is the mass moment of inertia about the principal diagonal of the cube, that is solid diagonal of the cube. And other two are of course perpendicular to that. But what is to be observed very, very carefully here, these are repeated eigenvalues, right? Because any 3 by 3 definite matrix would have 3 eigenvalues, 3 roots of the characteristic equation. But what happens, how do you interpret if the roots are repeated? Now, if you use a typical online calculator, you get these products. Please remember that since eigenvectors are mutually perpendicular to each other, these are unit vectors. Of course, since they are derived from the homogeneous set of equations, they cannot be defined in their entirety. So these are 3 unit vectors. And if you take the inner product of any two vectors, when I say inner product, it is the dot product. Obviously, cos 90 being the angle between them, the dot product obviously goes to 0, right? And if you observe that that holds for only two set of vectors. For example, if I take -1 plus 1 goes to 0 and 1 into 0, 0, this is valid. And if I take the dot product, it is plus 1, 0, 0. For these two vectors, the dot product is not 0. That means we haven't got the set of vectors which are mutually perpendicular, so they are not linearly independent. So let's look at this particular case. How do you go about it? Now, I have got two vectors, and I would find the third vector in such a way that this vector is perpendicular to the other two vectors. When I do some basic algebra and then arrive at this, I get this particular vector, and you would see that this is actually perpendicular to the remaining two vectors. So the requirement of orthogonality is actually satisfied, right? Now let's come here. And if I normalize these vectors, because if 1, 1, 1, then I would divide that by root 3. And it is easy to explain that if you consider a cube and if you calculate the direction cosines of the solid diagonal, which is from this corner to this corner, you would see that this is inclined equally to x, z, and y axis. And as a consequence, each angle, that is cos phi, if you say, it is 1 by root 3. So when you normalize, you get that 1 by root 3 is 0.5757. And similarly, you can divide this vector by root 2. You get these two. And then the third vector could also be divided by root of 2 square is 4 plus 1 plus 1, that is root 6. When I did that, I get this vector. And look at the question. The candidate was not only asked to find these vectors, but was also asked to construct the transformation matrix using this. And coordination transformation is applicable to any tensor, and this is basically the nature of the equation. You are seeing it here. It's an orthogonal transformation matrix, inertia tensor, and then transpose of that matrix. What I am doing essentially here is I am putting my first set of first eigenvector in the first row, second eigenvector, and the third eigenvector. When I do that, in fact, you can see that my principal inertia tensor is getting reduced to inertia tensor is getting reduced to principal inertia tensor, that means I am getting the three principal inertias. One, of course, about the solid diagonal, and about other two axes which are perpendicular to the solid diagonal. It is easy to interpret. Why am I getting 11 ma square by 12? Because through the solid diagonal my inertia is ma square by 6 plus m into if you calculate the distance from CG to the origin, it is root 3 by 2. If you square it up and simplify, you will get ma square 11 by 12. Okay, it is easy to interpret. And you can see that even if you were to calculate the reverse of the third eigenvector, that means instead of minus 1 in your algebra, if you were to calculate 1 minus 2 also, you can see that the transformation again yields us to diagonalized principal inertia tensor. Diagonalized inertia tensor, or you can simply call it as principal inertia tensor. Now we'll choose one more example to physically visualize this. Of course, you can use GeoGebra or MATLAB, a lot of free mathematical tools available on Google, and you can in fact see how whether they are orthogonal or not. And more than mathematics, using of MATLAB, Maple, GeoGebra is very important, because that builds a lot of visualization and detailed understanding. Look at this particular simple vibration example. If you simulate this in ANSYS, you will get repeated roots, right? That is because of the symmetry. See, this rotor is vibrating in vertical plane, and this rotor is vibrating perpendicular to that, is in the horizontal plane. The eigenvectors do not repeat. That is very important. Eigenvalues repeat, eigenvectors do not. And you can see that the second flexural mode also repeats, but again in different planes. So this is one more example. So thus, in vectors, you can find lots and lots of applications for mechanics. And especially if you buy our e-learning course, which is almost made quite affordable, $500 per month. And that is going to complement with a very, very detailed theory, lot of case studies, and multiple levels of assessments which are very, very critically designed. So that is going to prepare you for every competitive challenge that is thrown at you. And of course, in the next video or webinar, we are going to talk about 2D and 3D motions, two-dimensional and three-dimensional motions. And that also would have a dedicated discussion time for latest GATE exams. So I think in the next 1 year, you would be mastering most of the concepts, both from product development perspective and also from competitive exams perspective. With that, I would like to thank all the participants for your kind support and time. We profusely thank the chairman ISTE, Dr. Suresh, and also my chairman, Shiva Subramanian. Thank you, audience. We would see you soon. That is 4th of October for your second webinar series. Thank you once again.